So my name is Brendan O'Flynn. My talk is point tracking with lensless smart sensors. Dr. Lizy is really the brains behind this project, who developed all the algorithms that I'm going to be reporting on today, and I hope I do justice to her and all the hard work that the team at Tyndall has done in conjunction with our industry partners, Rambus, based out of the States. So today I'm just going to talk a little bit about why we're doing this research and how it fits into the research agenda of the Tyndall Institute and the Wireless Sensor Networks Group. I'll talk about the Rambus technology itself, how we're using it to develop sub-pixel level point detection to enable 3D point tracking of light sources. And then I'll show a little bit how we're fitting this into our research activities in Tyndall in real life experiments. And I'll talk a little bit about the accuracy of these systems. So Tyndall is based in Ireland. We're based down here, down in the south of Ireland. We'll be having an IEEE conference next summer to which you're all invited to submit something. And this is we're part of the University College in Cork, and we're 500 researchers thereabouts, working in very many different disciplines. So we have chemists working in conjunction with nanotechnologists and computer modelists. And my own group there is working on embedded systems, looking at the hardware, software, co-design activities associated with building sensors into the world around us. So it's very, very multidisciplinary. And my own background is PCB and hardware development and multi-chip module development. But this work focuses very much on the software aspects, some of the algorithms that we're developing to take these data sources from our different sensors that we're integrating into our systems and creating information from them. In this case, it's about location and point tracking of light sources. So as part of our Internet of Things agenda, we're taking lots of different types of sensors and building them into many, many different applications. Some of them focused on healthcare, fitness and health monitoring. Some of them developed on developing the communications platforms of the future and integrating and developing standardized communications protocols and developing non-standardized systems. The whole area of agri-food and the environment and sustainability is something that's really important to us as an application area, as is the whole area of building energy management in factories in the future. And we're active in all these different areas, integrating different types of sensors into our systems. And this is one particular research project which is focused on wearable systems, in particular looking at human motion tracking, and in particular in this case using the Rambus technology to enable a human-computer interface system. So this is what we're doing. We have our Rambus lensless smart sensor. It's a new next-generation optical sensing system, and we're seeing, can we establish with enough accuracy point detection of multiple sources of light to enable gesture recognition as part of a human-computer interface tool, as part of our virtual reality and our augmented reality system. But it all boils down to how accurately can we track points in 3D, in X, Y, and Z plane, and track multiple points to enable gesture recognition and various different machine learning algorithms associated with integrating people with this, or bridging the gap between this analog world of humans and the digital world of computers and augmented and virtual reality. So right now, we have this exoskeleton type system, which is really, really accurately measuring finger joint positions using inertial measurement unit technology. But in conjunction with that now, we also have these IR LEDs built into the system. So not only will we have very, very accurate positioning of fingers and gestures from that perspective, but by integrating this type of lensless smart sensing technology and point tracking technology, we also now will have positioning of the hand. So it gives you the full range of motions to enable people to interact with the digital world. So effectively what we're trying to do is we're trying to replicate some of the expensive Kinect full CMOS camera systems that are currently being used to track and monitor motion. And we're trying to replace them with our low-cost smart sensor system based on a low-cost manufacturing methodology. So we're replacing this, but keeping the same functionality. And this is the Rambus system itself. So this is our traditional optical-based system. A lot of the form factor and the size and the cost is in this part of the component. So down here is your typical CMOS sensor. And then in your optical imaging system, the standard-based system, we all have all our enclosures, our windows, our lenses, our focusing motors. And we can do away with all of that in our lensless smart sensor module. So it's very, very low cost to manufacture. It's a wafer-level packaging compatible technology. By replacing this by replacing this optical imagery with a diffraction grating, because this is how the Rambus system works. So that's our reflection grating. The light comes through onto our CMOS sensor and creates a diffraction pattern, which is basically a spiral. when we have multiple pixels in our system, these spirals combine to give a blob. And through appropriate phase masks and Fourier transforms, we can reconstruct the image from that blob in a computed image. And what we're trying to do now is see how accurately we can track individual points of light associated with each individual pixel and that CMOS array based on the spiral that's being generated by the Lensless Smart Sensor. And this is what we have. So this is the spiral. The light, this is an individual pixel, so we have two apertures on the version of the Lensless Smart Sensor that we're using at the moment. So we have this dual spiral binary diffractive pattern. And when we develop our Fourier transforms and reconstruct the image, this is the point that we're generating. So we want to be able to track and see how accurately we can position that in the X, Y, and Z planes. So to enable the highest possible accuracy, we're looking at ways of seeing, so if this is the center of the pixel, generally the point source of light is slightly offset from the center of the pixel. And to maximize the accuracy and the positioning capability, we want to see how big that offset is. And this is called sub-pixel level detection. So we need to find out effectively what is the delta X between the center point of light and the center of the pixel. So there are a number of ways of doing this. So there's a ratio-based method where it's a linear relationship between the center point of light and the light intensity as it goes out towards the periphery of the point source of light. Another estimator is the Gaussian estimator, which assumes a Gaussian fit between the point source of light at the center and the light intensity as it goes out to the edge. And then there's a linear interpolation model, which also assumes a linear relationship. So we investigated different levels of accuracy associated with each of these methods to see what was the most accurate method of estimating the delta between the center point of light impinging on the pixel of the image sensor and its actual position. So the experiments that we carried out were at a Z of 50 centimeters away from the sensor plane, aligning the sensor with the focal point of the detector. And we found that the Gaussian estimator technique was the most accurate, giving a sub-centimeter accuracy. Not only that, but because we're looking at developing these systems on an embedded platform and minimizing the execution time associated with all the calculations that we're doing, the Gaussian estimator fit was the most accurate and was the fastest system in operation. So we chose that one for our work. So now that we know where the light sources are, we know where the pixels are, we need to establish what is the X, Y, and Z coordinates associated with the point of light as it's moving in the plane in front of the focal field. So we have our right sensor and our left sensor, and we're trying to establish what is the position of this point source of light. Effectively, it all comes down to trigonometry, Snell's law of refraction for the individual components built into the CMOS sensor itself. The equations are all in the paper. But our calculations of Z and our experimental process was then used to figure out how accurate we were able to calculate X, Y, and Z, these trigonometry-based measurements based on a real experimental platform, so that we could then start using that as part of our motion capture technology. So in the first instance, we used an unknown Z. In the first instance, we characterized the system for a known Z, a known X, a known Y, and we're able to establish and validate the algorithms that we were using. But in real use, in real life, we're looking at using an unknown Z, an unknown X, and an unknown Y as the point source of light, which is based on the hand, moves around within the field of view of the sensor system that we developed. You can see the levels of error that we have here. So when the point source of light is in line with the sensor, you can see the level of accuracy is very, very high. But as we move away to the left and the right of the center of the sensor, you can see how the accuracy of the system degrades. And as you move out on the Z plane, the level of error increases quite dramatically. We can see that when we keep the Z constant and we move the system in the X and Y plane, the level of error as we move away from the center of the focal point of the sensor, the error increases in a symmetrical form on either side, plus X, minus X of the sensors. And because of this symmetry, we were then able to develop a compensation algorithm to increase the accuracy of the measurements that we were taking. So we developed a polynomial fit function to calculate the coefficients of the fitting curve. We validated this with a large series of measurements, and we could see that through various different experimental sets that we did, that we were able to increase the accuracy of the system very, very dramatically. So if you remember two slides ago, this was the types of level of accuracy that we were getting. Our polynomial fit function was able to reduce the error very, very, very significantly. So it's very close to zero, right the way up to 70 centimeters away from the focal plane, and even at a full meter away from the sensor, the LSS sensor system that we developed, which is well within the realm of a human-computer interface tool. The levels of error are very small. Specifically, this compensation algorithm reduced the error to less than 2 millimeters along the x-axis at the center position. In between the two sensors, the level of error never goes above 3 millimeters. Along the z-axis, as we change the field of view to 80 degrees on either side of the center of the sensor, we can see that the level of error is less than 2 centimeters in all cases. And this makes it really, really appropriate for motion capture analysis in conjunction with other inertial measurement hybrid type technologies. So, just to summarize, these lensless smart sensors, they're very small form factor, they're inexpensive to manufacture, and they do offer opportunities for point tracking. So the accuracy of the 3D point tracking algorithms that we've developed through using these Rambus sensors is improved by sub-pixel detection, and our compensation algorithms gives sort of millimeter level accuracies, which makes it very, very compatible as a human-computer interface tool for multi-point tracking. And we're now in the process of integrating this technology into our wearable systems to enable this augmented reality human-computer interface system to be developed. So this work was done in conjunction with Rambus. Our key partners in the project is funded by Science Foundation Ireland, and this is Dr. Abram with the system at a recent outreach type event where she's showing children how she can use this Rambus system to draw an interface and with the computer. So you can see the LSS technology in operation here. And where we want to go with this is combine it with our inertial measurement unit system, which is the exoskeleton system that you saw pictures of before. And you can see this is limited to just joint angle position. It doesn't give us true positioning of the hand in space. The combination of these two systems together will give us full point tracking, positioning, and finger motion in a human-computer interface system. So thank you very much.